Hi, welcome back. We are writing a mini Rust in Rust. We're doing it just for fun, not for any other reason. This is video 6. We're going to see if we can get to the point of parsing something. We've been doing a bit of lexing, and we've done a whole lot of error handling and refactoring to make the structure of it look right. So we've got one more thing we need to lex. I want to be able to lex an expression that we can then parse, right? So I want to be able to lex like a plus sign so we can parse. So lex, let's say lex addition expression, that'll do for now. So we're going to try and lex 17 plus 65, right? So we're going to invent a new type of token. I think I'll call it, should I call it plus or should I call it, I just don't know. Should I call it operator? Let's try calling it operator and see how that goes. So yeah, if you give it 17 plus 65, it should say there's a 17 and a plus and a 65, right? In fact, we said we would change the numbers every time, didn't we? So let's do a short one. Let's do 3 plus 550, just for things. So first thing we need to do is make ourselves this operator function that makes a token of a different type. And I think there's going to be a pattern if we take in the literal that actually created this thing as part of the thing. And this is going to return an operator. And maybe later we're going to want to know what the operator type is instead of just holding the literal inside there. But for now, this will probably do us. So we need to say, as well as ints, there are operators. Yeah, I can very much see us, instead of a string, or as well as a string in here, having like operator type or something. But whether we want to do that at the lexing stage or the parsing stage or whatever, is still up in the air. So for now, we won't do more work than we need to. It's just warning us that no one uses operator, which is fair enough. So we just, oh no, in our test code we did. Yeah, okay. So interestingly, why is it not warning us that no one's constructing an int? All right, let's not get distracted. Fine. I'm sure we'll sort ourselves out soon. Yeah, so this is how we make a thing. So if we run our tests, we should see our test fail. Yeah, because it didn't. Oh, look at this wonderful error message, right? It says this plus is not what we expected. Also, another test failed. Panicked on an install error. All right, let's look at line 147. I mean, I'm really confused. Oh, I guess maybe once you've gone wrong, Miet doesn't like us reconstructing another Miet. Maybe something like that. So let's ignore it for now. Hopefully it'll go away. And maybe there's a better way of setting up Miet instead of doing it inside here like this. So we'll think about that. Okay. So this is failing to lex because plus is not recognized. So let's make it recognized by looking at our lex function, which is all the way inside here. In fact, it's the, next on the iterator ends up calling lex next. So this is the real bit. And at the moment we're matching on the first token, first character in a token. So there's going to be another thing that we match on, which is a plus. And actually, we don't even need to call like a sub function to like process the rest of the characters, because there are no rest of characters. It's gonna be it's gonna return okay. Oh, hang on, this is the wrong place. We should do this here. It's gonna return okay of. Oh, it's already wrapped up. How are we getting our? Oh yeah, I was just getting confused about where the option's coming from. The option's happening here. So it's quite straightforward. It's going to be token operator, I guess capital O operator, and it's going to be turn this character into. So what I'm actually going to do, let me show you a feature. I'm going to give it a name, even though we know it's exactly plus. I'm going to give it a name here, and it's not a string, so we'll deal with that in a second. So this op at means name the thing you're matching op. The reason I'm doing that is because later this might be a plus or a minus or a times or something like that. So it feels worth putting the subtraction in here. And now the problem is this is a char and it should be a string. So we could do maybe 2 string on it to make it into a string. I mean, this allows for the fact that operators might one day, there might be some operators that have multiple characters in them, but for now we've only got one. So I'm balancing, you ain't going to need it, with just a little bit of an eye to the future without this hopefully getting too crazy. But I'm not actually adding in the minus or anything like that because there's no tests for it. That's my rule, right? Like, you don't write code that there's no tests for, but you can have an eye to the future. So that's what I'm doing here. So now with any luck, that might be as simple as that. Oh, no, yeah, it doesn't know what to do with the space. Yeah, so normally, if we, when we were reading in an int, we were consuming the space at the end of it. And that was the way we were kind of understanding that it had ended. So this is all going to have to be fixed at some point. But for now, I think what we can do is just say, if we hit a space, then I guess we do nothing. Oh gosh, we don't have a way of saying skip this, do we? I guess we'd have to call lex next again. Is that going to work? Not sure about that. Yeah, it returns a result, so we'd have to like returns an option. Is that going to let me do that? Yeah, okay. So I guess we could just return, instead of that question mark, we could maybe just return that. Is that okay? Yeah, so I'm not particularly happy with this, like jumping out from here in order to recurse on itself. I think I'd prefer if this bit of stuff was in a separate function and that function was recursive instead of recursing into lex next, which feels a bit wrong somehow. Let's see if that works. We can always refactor later. All right, so it's good enough for us for now that we can now lex pluses and we can skip spaces. So I guess I want a comment here because this is a bit confusing. Skip spaces. Just recurse into this function for the next character. Something like that. And then this is anything else we don't recognize yet. So I guess we just have a little comment here for integers. Integers start with a digit. In future, other things might start with a digit, which is why that's not quite such a stupid comment as it sounds. And operators. Let's just say operators. All right. So that feels like a commit, doesn't it? Okay, I don't have anything checked into Git yet. I don't know what on earth I've been doing. So let's do something now. So we should do much better Git commit discipline than that. Basic lexing, let's say. Right, so our next step now, we've got a lexer that can lex this expression that we had. And I will split the, so now we can lex this. I will split this lexing module into a separate file. I'll probably do that off video since it's not particularly interesting. But I'm going to make a new module now called parser. And it's going to parse stuff. And up until now, we've been able to, what is it like? Oh, we had to echo, didn't we? So pipe something into the program. We can do 3 plus 7, and it should print out the lexed version of that, 3 plus 7. Now I'm going to change it, so it's going to be able to parse and lex. And it's going to print out the result of parsing as well as lexing. In order for that to work, we need a function called parse. And then we can import it here somehow. Like I say, I'll move these into separate files. Parser, parse. And that needs to be public. And what a parser does is takes in a stream of tokens. So this is going to be input iterator, where the item is a token, and it's going to return, I guess it's going to return a parse. What do we do with lex? Oh, it has a lifetime. We're probably going to have lifetimes here, aren't we? So maybe it's not. Maybe it's going to take in a lex because it has to have a lifetime on it. So I think it's going to look like this. We have a lifetime, and we're going to use the lex from the lex crate. And we're going to have our own structure here called a parse. And this is going to be basically an iterator, same as lex is, I think. It's going to be an iterator of syntax trees. Like so. That should be tick A. And we don't return 1, so let's return 1. Like so. We're not using the input yet, but that's fine. Complaining about that because we're not actually using it. And yeah, I guess it's going to hold on to the input, which is, we already know is a lex of tick A. So input is going to be like that. So we're skipping the step we did before where we wrote this kind of manually and then turned it into an iterator later. And we're going to make it an iterator right now. And we're going to import iterator for, so we're going to do something very similar to this. We haven't said what lex returns yet, have we? We'll do that right here. Yeah, so we're going to import iterator for parse, and the item type is going to be a result of syntax tree. I guess we'll call it that for now, and we're going to call some kind of function called parse next to actually do the work. And we're going to need to define a syntax tree. Where did I do this in the lexer? I did it kind of near the bottom. So we won't talk much yet about what a syntax tree is. Is it an enum? It's probably an enum, but we'll see. Even that might change. Haven't thought about it. It probably also uses a lifetime, because it's still going to be referring to bits in the original string that we were given. And this parse, so where am I putting the parse function? Put it at the top maybe. And then we're going to import the parse object, struct, and provide this parse next function, which is following the same structure as last time, and that returns an option of get result of syntax tree of that lifetime, like so. And this should have that generic param init. Right, so I think we're almost done with the setting up. Parse next. I guess it should probably take a mutable reference to self. But what's the problem? Not finding a parse next. Oh, that's because I've done something wrong here. I missed out one of the diagonal brackets. Yeah, I think that's right. So now we've got to implement parsing. So for now, let's just say none, right? And then we can write a test for our parser. So let's not worry yet about how syntax tree doesn't use its lifetime. Instead, let's make a test. And I guess the most basic test will be like parsing nothing gives us an empty list. Parsing no input returns an empty list, something like that. So we're going to have our own, I'm pretty sure, function a bit like that lexv called parsev of an empty string. So it's going to be a set eq. Parsing an empty string gives us an empty list. Something like that. And parsev is going to lex and parse something and give us back a vec of results of... No, it's going to give us back a vec of syntax tree. We're going to just get rid of the possible errors. We're going to like unwrap the errors in here, something like that, I think. Let's just look. What do we do for lexing? We collected them. Oh yeah. We did. We pulled all the errors out to the outside instead of being inside the vector, and then we did an expect on it. So we're going to do something similar to that. Really need to break this into separate files. It's getting a bit unwieldy. So we're going to be parsing our input, which is going to be a str. I mean, it's going to be a tick A str. Is this what we did? No. Oh, I guess it was implicit. Oh no, tokens don't actually. I think that's wrong. I think tokens are going to have a lifetime, but we'll see how far we get with this. So parse is going to return as a vec of syntax tree, or result of syntax tree. Let's import everything from there. For now, let's get rid of this lifetime to make things look a bit easier. And syntax tree needs to derive debug for us to be able to use it in these tests. And partial eq, I guess, so we can compare it. What else? Right, now parsing, we need to lex it first. And we need to bring in the lexer to do that. And what does lex return? Lex returns a lex. Oh, of course. And the parser takes in a lex. And a lex is when you iterate over a lex, you get these results. All right, so the parser has to deal with the fact, if it's going to take in a lex, the parser has to deal with the fact that some of these results might be actually be errors. So I'm not sure a parser wants to deal with errors, does it? So probably we want the parser not to take in a lex, but to take in just an iterator of tokens. Let's see how that goes. Token like this, and these lifetimes I've added in unnecessarily. Like at some point we're going to need them, I think, but let's not do it now. It's just making our life more difficult. So it's going to take in an iterator of token. This should be an impl iterator of token. Iterator item equals token. And I guess we're going to put it here and say where I is an iterator with a type as token. We might not like this. This might all change again, but we'll see. So parser holds on to that iterator. Doesn't need the lifetime anymore. Oh, that should be item, I think. Yeah. We need to bring in token. And parse needs to be maybe we need to be explicit about the iterator type. What if we just said, just figure it out? Now, this is just wrong, so we can get rid of that. So yeah, we're changing, for now we're changing for that lifetime, but we've still got a generic parameter, which is like, what is the input type? Yeah, so where I is an iterator, item equals token, and syntax trees don't have lifetimes yet. So what are you complaining about? We need to say that here as well, I guess. I'm going to regret this when I change this and we have to do it all over again. Right, where have we got to? Looks good. So yeah, basically errors that happen in the lexing stage need to be dealt with before we move on to the parsing stage. I feel like there should be more errors than there are. Okay, yeah, we've got some kind of weird compile error, which is why we're not seeing more useful errors. So what is it saying? Cycle detected, computing the variances for items in this crate. Okay. So it basically wasn't able to analyze it because of something to do with all the generics that we're using. So what should we do about this? I think it's maybe, I don't know what that underscore in here means. So let's just do it the same as we've done elsewhere. I is an iterator with an item of token. Maybe that will sort it out for us. Yeah, now we're getting more normal looking errors. Okay, so whatever I did to say just figure that out for yourself caused some kind of cycle that made it got very confused. So now we can't call parse on the output of lex because lex returns an iterator of result. So what we can do is let tokens equal lex whole input, and then let's just make it be a vec of token and collect. No, that's going to confuse it. Let's make it a result of vec of token, like so, and call collect on it. I guess what we want to do is somehow like adapt. And I'm wondering, do we want the errors to just continue? Do we want to call parse even though there were some errors during lexing? I think we don't, so I think this is fine. So let's bring in token. This should be a miette result. And again, I'm not naming just result because I don't like bringing in a result that overwrites the result that's already there. And we still can't pass in tokens, but what we can do now is we can unwrap tokens, or we could make some kind of iterator. But this is fine. This is fine. So let's do an expect here. Just say lexing failed. In fact, no, let's do a question mark on it. Let's do a question mark on it. So this is just parse. Yeah, okay, this is right. This is right. Because now that means that this miette result gets passed out to the... All right, I said it's right, but it's not working. Okay, yeah, we have to iterate over it. Well, I guess into it, right? Come on, that must be right. Okay, syntax tree needs to be public. That's the kind of error I can get behind. So yeah, basically lex it all, collect it up into a result, and then question mark it to say if it failed, return immediately. Otherwise, turn it into an iterator so we can give it to parse and parse can deal with it. So this allows us the possibility. So right now we're pulling all the tokens into a vec. But it allows us the possibility of not loading everything into memory at all at any point during our process, apart from the original string, which we did say we would read into memory. But this doesn't need to be a vec now. This can be an iterator that bails out as soon as it hits an error. Yeah, so that will be a little bit of a mechanism to make that work, and it won't be as easy to understand as this. So I'm not going to do it right now, but it means that we've structured our code in a way that it can be pretty frugal with its memory, even for a very long program. And just feels right. It feels right to me for a parser to be like a stream of tokens that come in and a stream of syntax trees that come out. So I guess I haven't really talked about what a parser does, but what a parser does is, given that you've figured out all the different chunks of program, which are tokens, it arranges them into tree shapes, which represent, in some sense, not exactly meaning, but they're like the structure of the language of your programming language. So, like, for example, this example we're looking at with 3 plus 7 or whatever it was, that's all one thing in some sense. It's one expression, which is like an operator with 2 arguments, a plus with 2 things being passed into it. So, that's, yeah. That's what it's going to be. So again, I'm just thinking now, I got distracted halfway through. Oh yeah, for our test code, this is totally fine for us to say, let tokens equal this. Dot collect. Again, we're going to ask, collect is doing the magic here of moving the result out from miette, which is why we need to declare it, right? Collect would normally like have a good idea what you wanted to get back. You just have to tell it needs to be a vec. But in this case, oops, we want it to take the vec of results that it would normally produce and produce a result of vec instead. So we'll give it tokens, but we'll question mark that and into iterate just the same as above. Oh, come on. Like so. And, all right. And in this case, we need to expect it because we're not returning a result here. And this should be lexing failed. And this should be parsing failed. Right, so if our tokens is a result, we failed to lex. Otherwise, turn it into an iterator, give it to parse. Parse gives us back a result as well, which we collect again into a result, and then we expect it. So this is just for our test code that we're going to crash if it all goes wrong. So our test passes. Yes, our test passes. So it's a pretty trivial test. I don't feel the need to make it fail particularly. We could put something in here. So now let's try and parse something really trivial. Parsing a number produces an expression. So an expression is basically a thing that's been parsed that has a value. So in this case, we're going to say 51 passes into some kind of syntax tree. I think this is going to be a what would you call it? Just like a leaf or something, like just a single thing. Let's call it a leaf, and I'm probably going to change that now because I don't like it. And the leaf is going to be, essentially it's going to hold, I think it's going to hold a token. So for now we'll do that. So this is an int token with a 51 inside it. Now we might want, at some point during parsing, this has got to be a string. At some point during parsing, we might want to turn this 51 into an actual number. Certainly, before we evaluate it, we've got to make it into a number. We could do that at lexing time to say, well, actually, if it doesn't convert correctly to a number, then something's gone wrong with lexing, so that's a good time to do that conversion. But we probably want to hold on to the literal too, because what if we support things like underscores in numbers and things? We might want to know that literal was a particular sequence of characters, so we probably will hold on to the literal too. But yeah, when it comes to evaluating, we need to actually get the number 51 somehow out of this. But let's say not yet. And yeah, there's no leaf yet, so let's make a leaf in here, which holds on for now to a string, which is just the no, holds on to a token. Yeah, so not most of these syntax trees won't hold on to stuff from the lexer, but in this case it will. Okay, so our test should fail, right? We've got a warning as well. Oh, unused import. Let's get rid of the unused import. The other warnings we're probably okay with for now. But yeah, we failed because we were trying to parse that number 51, and it should have been a leaf containing an int token, and instead it's an empty list because we've done nothing yet. So parse next now needs to do something. And I guess the simplest thing it can do for now is just always return a leaf of the token it's been given, right? Oh no, so we need to actually get it. So we need to do self dot input dot next, and it's either going to be something, or so I guess we could do self.leaf.next.map. I get very suspicious of any use of map that is not completely trivial because it gets really confusing, but I think in this case we can get away with this should be an okay, I guess, syntax tree. So just in case you're not familiar with map, so next returns an option, so it's either some or none, and then map on an option says if there's nothing in there, if it's a none, just immediately return a none, but if there is something in there, give me that something, the token inside the sum, so that I can do something with it, and I'll give you back something which then you wrap up again in sum, so that means we get our option as our return value here. That's exactly what we want, right? So if input.next gives us a none, that means we finished lexing, so we should return a none because we've also finished parsing if we finished lexing. Okay, so our first test passed because it was trivial. So what happens if we parse an expression containing 3 tokens? And now we need to think about how we want this to look. So we're going to do something like 82 plus 1. And that should come out as a syntax tree, which is I guess we're going to call it an operator. And the operator is going to consist of an operator token, maybe, probably. So this is going to be some kind of token operator with a plus. We should actually, I would prefer to call our little functions that we made, right? So these two owns can go away. We might need to make them available, but there's nothing wrong with making them available. The fact they were test only was really just a convenience. What have I done wrong? Oh, yeah, this should be passing an expression. Passing a sum produces an operator expression, let's say. And this should be produces a leaf expression. So let's make token int and token operator be not part of the test code, but be part of the main way you deal with tokens. Make them public. That means I'm allowed to call them. We'll deal with that in a second. I guess we'll deal with it now. So let's make a syntax tree operator. And that consists of a token. Oh, let's name these because it's getting confusing. So it's going to be an operator, which is an operator, which is a operator token really, and then left. And it's not; these are not going to be tokens longer term. They're going to be syntax trees. Let's make them now syntax tree. So the point is, the left-hand side of an operator might not be just one token. It might be a whole set of operations that are themselves a syntax tree. Now, you can't do this because it's recursive. So we need to make this be a box of syntax tree because it doesn't know what size a syntax tree containing a syntax tree containing a syntax tree containing a syntax tree is. So we need to have a pointer to a syntax tree in here. Okay. Now, what errors have we got? So, yeah. So this, we were making an operator, but that's not how you make an operator. By the way, there is a question here. Should the operator also be a syntax tree? And the answer is maybe at some point we would want to have an expression that resolved down to the plus operator. That would be quite unusual in a language. So we definitely won't think about it now. It's not something you can do in Rust. You can't have 3 and then a bracketed expression that eventually becomes a plus and then 5 or something like that. But it is something that you might want to do in some languages, so it would be worth thinking about. But yeah, I imagine it would have unpredictable results. So this is going to be, we said that left was a syntax tree, and let's for now say, well, no, definitely it's going to be a leaf, which is itself a token int 82. So you can see that this what we want to produce kind of is fairly straightforward. We want to create, when you parse 82 plus 1, you should get an operator which consists of the type of operator is a plus, so like the operation you're doing is a plus. So maybe this should be operation, just to make it a bit easier to understand. I don't know about that. That might be making life too difficult. And then it's got 2 syntax trees inside it for the 2 expressions, left and right. And this should be a box. We're going to be a bit sad that we have to box things up, aren't we? But in this case, it's a recursive structure. There's probably no alternative I can think of. So yeah, when you find, say 82 plus 1, that's actually an operator consisting of an operation and then 2 expressions on either side. And in this case, the 2 expressions are both just leaf nodes, but you could imagine 82 plus open bracket 17 minus 3 or whatever, in which case this wouldn't be just a leaf, this would be another operator or something like that. And we need to think also about what we do with strings of operators, so we'll get to that too. All right. So now we have a test stating what we want to happen, but the question is, how do we write a parser that produces that result? And that's where things get interesting. Yeah, so notice what we get out of this is we get 3 leaves. So the syntax, instead of becoming one operator, it's just gone, oh, every token I see, I turn that into a leaf, because that's all we've written so far in our parse next function. So, where is that? Where did I write parse next? Yeah, okay. So yeah, well, at the moment what we do is every single thing we get, we just return a syntax tree leaf. So already I want to lose this map thing, it's just making me sad. So we're going to do it the old fashioned way. If let, if we were given a token, then do something. Otherwise, don't do anything. And then what we were doing before. So what we're going to do is match on the token. And this is going to look, hopefully it's going to look a lot like the parser. So if the token is well, what are the for now, to make this work, all we need is if it's a int, yeah? So we're just going to match on if it's an int with some kind of, in fact, we don't care what's in there, we're just going to get hold of this. Well, we've already got the token here, so probably we don't need, yeah. So then if it's a token, which is the only thing we care about for the moment, then we're going to say, well, for now, the only type of thing we can parse is an operator. I think it should be called operation here too. And I think the thing itself, where is my struct, my enum? I think it should be called an operation, not an operator. And in fact, this should be called operator, I think. Operator or. So I'm going to change my mind so many times while we're doing this, but yeah, all right. So match the token. If it's an int, then do something. Otherwise, we're just confused. So we'll do an error. Now let's go and look at what our error in our parser looked like. Here. It's going to be really similar to this. So I like the fact that our parser and our lexer are going to look pretty similar. If it could be the start of an operation. No, this is going to be, let's not write a comment here because it's going to change, right? The operation is not the only thing it might be. So we'll get there. What's it complaining about? Oh, yeah, that should be like that. No, it should be self.next, right? Yeah. No, self.input.next. Don't want to call self.next. That would be very weirdly recursive. All right, so we haven't got an operation thing. All right, so this should be unexpected token. And we need to bring some stuff in here. And the label, like, it's basically where in our input. So I guess it's going to be the token. The token itself is going to have some kind of span or something to say, like, what characters does this token start and end with. So let's just to do that. But like I said before, it's really important that you get the error handling done early. So we're definitely going to handle this to do soon. So now unexpected token needs to be defined. So let's have a look at unexpected character and try and define something similar. Where did I put that? I guess let's just put it near the bottom before the tests. We're going to call this unexpected token. So this is just the error that we print when something we didn't know, we didn't expect it to happen. It's going to say this token, and all this stuff is going to get imported from yet, I hope. Like so. Yeah, so basically this is going to say, I didn't know what to do with this token, and we're going to have a little label pointing at that token. But we'll get the little label pointing at the token soon. Now, the name, we never did the name of the file or anything like that. But the source code should be, yeah, I guess this should be, again, we don't have this yet. So again, we're going to do this. And for now, we are going to pretend that we've got some kind of source code here. And it needs to be a string, I guess. Now, we are returning our answer, so that's why it's getting complaining about that. And this should be an option. So yeah, what do we do in Lex next? We get out a thing, and then we handle the summing afterwards, don't we? Because we might have hit an error. So let's not worry about errors this video, and let's just return some error. And then we'll have this return sum operation. In fact, yeah, let's wrap this whole thing in sum. Like so, and then we'll do better later. So we can get rid of the one we added here. And now we need to implement this operation function. Oh, that's no good. We can't wrap the whole thing in sum. We need to wrap this in the sum. Yeah, because that bit is not a sum, it's a none. Oh, fine. All right, so now we need to implement the operation function. It's going to take in a mute self because maybe. Yeah, in theory, yeah, because it's got to read more tokens in. And it's going to return a result, a met result, a result of syntax tree. And let's do something dumb for now. Let's just return syntax tree leaf, even though this is an operation thing. And we need to pass in the token that we had. So the first token we hit is definitely going to be used. So we'll pass it in, just a token, and we'll just say, for now, we'll just say it's a leaf. Even though that's not what we're expecting here. That should be an OK. And we've got compiling code again, so let's test it. And we got a parsing failure, an unexpected token, because we hit a plus. Now, obviously, the error message is all completely wrong because we just faked the error message. Next video, we'll sort that out. But what happened, I'm pretty sure, is that we hit an int, we dealt with that, and then we hit the plus, and it didn't know what to do with that. And that's because we expect operation to handle that. So the dumbest way to do that is to say, get me 2 more things from your token stream. So we've been given 1 token, which we figure is part of an expression, part of an operation, because operations are the only thing we can parse. So the next thing that's coming is a plus. So we can say let operator equals self.input.next. And in fact, we can say if let sum operator equals self.input.next, then do something. Otherwise, something bad happened because we're expecting an operator. We think this is going to be an operation, and we're expecting an operator, and we didn't get one. So that means it wasn't an operation. So actually, this function really should be called operation or leaf or something like that, shouldn't it? Because it maybe there are no more tokens, in which case we finished parsing this thing and it was a leaf. So let's try writing it like this, leaf or operation. Because all we know is we found a number, right? So that could be just a number and that's the end of the statement or the end of the expression, or it could be part of a bigger thing. So if there was no token afterwards, it was just a leaf. I guess it should be an OK wrapped around here. And the leaf should just include the token we were given. And we're done. Otherwise, it's either going to be, operator is either going to be another number, which doesn't make sense, like two numbers one after the other is bad, or it's going to be an operator, in which case we're still on. So let's handle both of those cases. Token leaf, sorry, int, that's some kind of error. So we're going to have another type of parsing error here. And it's going to be, I mean, is it just an unexpected token at this point? For now, let's see, like what I plan to do at some point is look at what errors Rust returns and try and emulate them as best I can so that we're writing a language that truly is approximately equivalent to Rust. So again, we're faking the error handling, but basically if you find an int after you just had an int, that's not a valid bit of syntax, so let's just write that down. 3 like that is not valid syntax. Right, and then here this is like e.g. 3 plus, right? So it's all good, but we haven't finished yet. We need something else to happen afterwards. And we're going to really dumb this down. So what we're going to do, in fact, what we're going to do is call out to another function. No, are we not? We're not yet, because this is all still one operator, isn't it? So we've got our plus. So now we're expecting some kind of right-hand side. And for now, we're going to just hope it's a token, just a token. But later it might be a whole expression, mightn't it? So we'll see. All right, so if we get something else from input, self.input.next, we're all good. If not, if we've reached the end of our tokens, then this is also an error. We can say e.g. 3 plus brackets end of file is not valid, right? You know, there's got to be something after the plus. So we can say, oh, it's not an unexpected token. This is like unexpected end of file or something. Whoops, what did I do? Let's try that again. This is going to be, no, come on, we can do this. Really lost. What happened? Yeah, try one more time. Get my Vim foo up to scratch. All right, so this is not going to be unexpected token. This is going to be unexpected end of file. Why has it laid it out a bit? Wait, oh, no, it's just got into a long line. Okay. So we need to define this thing called unexpected end of file. We'll put it next to unexpected token. And we're going to deal with the fact that we expected more stuff. So what can we say about this? Expected more tokens. Expected more code. I mean, we reached end of file. Reached end of file mid expression. Hopefully that's a friendly-ish way of putting it. And then we can just say here, right? And it's going to be like the end of the token or something like that. We're going to point at. But we're not dealing with errors this stream because it's too difficult. All right. So now, if all went well, we did get another token. So let's match on that right-hand side. This has got very nested, hasn't it? Maybe, I don't know if it's too nested yet. It's very close to too nested. Okay, so let's match. Let's just have it fill in what could be here. So if it's another operator, that's bad. There's going to be an error. But if it's an int, that's good. So let's go for, we've got right hand side already, so we can just say now we're done, right? If we found another int, for now at least, our expression is finished. So we're going to return a syntax tree operation. And we've got all the information we need to make that syntax tree. So we've got an operator, which was the op thing that we got. And we got a left, which is, we need to wrap it in a syntax tree leaf because it was just a token, wasn't it? That's our token. Maybe this should be renamed left-hand side or something. I don't know. And then the right-hand side is also going to be a syntax tree leaf of this thing we just got here called right-hand side. And we need an OK wrapped around this. And what's wrong here? Oh, this should be... Oh, this should actually... We want operator, not op. Oops. In fact, maybe we can just say operator like that. And then I don't think we need to name op because we're never using it anywhere, right? Yeah. All right, now what's it complaining about here? Oh, it should be a box. I wonder whether we can think of a way of not boxing this stuff. I mean, naively, there is no other way. But maybe, I don't know. Anyway, let's not worry about it. And now, this to do, we can actually fill in because it is, it's going to be another error. So let's fill it in to the extent that we have the others. This is going to be, basically, you can't do. So this is going to be e.g. 3 plus plus is not valid, right? Because we got another operator off. We've already had an operator. And this is going to be e.g. 3 plus 3. And we're all done. For now. Later, you'll be able to have more stuff after that. All right. I think if we can get this to compile... it should be called leaf or operation now. Then I think our test is going to pass, and if so, we're going to be very happy that, what's it complaining about? Oh, they never used. Okay, don't worry about that. Okay, our test passed. Look, parsing a sum produces an operator expression. All right, so I know this is a very minimal implementation. You might think that doesn't look much like a parser yet, right? I mean, it kind of does a bit, like it's deeply nested. But yeah, it's kind of saying, like, yeah, I've either got a leaf or an operation. So look at the next thing that comes at me. If it exists and it's an operator, we're all good. We have got an operation. If not, there's some kind of error. And so get the next character, so next token, and it should be like a number. So if it is a number, then we're all good. We found ourselves an operation. And then we've got a load of possible cases that are not valid, where we've got horrible errors that don't really work. So we are able to parse. Let's try this. We are able to parse 3 plus 7. And previously we were printing out the tokens. Now we're printing out the parsed stuff. So now we've got an operation which is a plus between a 3 and a 7. And we can also just do just a 3. And look, that's also recognized because we said that we wrote that leaf or operation thing. And it comes out as another syntax tree, which is just a leaf of an int of 3. So we genuinely can parse, like there's only 2 types of thing we can parse at the moment, right? Numbers and operations. But we are able to parse them fairly flexibly, like we can put in a longer number. Not negative numbers yet, but we'll get there. And you can see it does say it's a plus between this number and this number. So we have got parsing working. I'm very glad. I was hoping we'd manage to do that in this video. And I think in the next video, we're going to actually work out these numbers, what they are, and add them up. So we'll have to start making decisions about, like, at what point do we take that sequence of characters 3, 4, 4, 4, 4 and turn that into an actual number that we know how to add up, and what do numbers look like. And like I said, for now, we're going to just copy Rust for everything it does. At some point, we're going to think about deviating from Rust, or optionally deviating from Rust, because it may be one of the purposes of this language is as a toy language to just think about what if Rust worked differently or something like that. But for now, we're using the convenience of having Rust there as a reference for us. That means we don't have to make a lot of decisions. We just copy Rust. And at some point in the future, we'll make a test suite which runs these programs through the actual Rust compiler and compares the output of our compiler or our interpreter with the Rust compiler and see if we can make ours match nicely to it. Hope you're enjoying this. We did finally get to actually parsing something, so I at least feel like we're on track. Yeah, if you're enjoying it, see you next time.